Hello guys, I am here to explain question number 3249. Count the number of good nodes. So here we are given an undirected tree with n nodes which are labeled from 0 to n minus 1, and we are given several edges. These are bidirectional edges, and now this is the tree that we have been given. Now they are saying a node is good if all the subtrees that are rooted at its children have the same size. For example, for this 0 we have two subtrees, which is one is this and the second is this. Both have three children, right? So this node is good. Same case for 1. For 1 the subtrees are 4 and 3, both have one total node each. For 2 it's same. For 4 and 3 these are leaf nodes, but they will be considered as good nodes because they have 0 subtrees, and 0 subtrees are accepted as good nodes, right? So we have to find number of good nodes in the given tree. Let's see the example 2 as well. For this node 3, for all its children nodes subtrees, the number is same, right? 4 and 8. 2 is not a children tree because 0 is the root, right? 3 is not the root, so that's why. And now here it is the same thing for 9. For 12 is a good node because 0. 10 is a good node because there is only one subtree. For 1 there are 3 and each have one node, right? 1 is a good node. 4, 3 and 2 are leaf nodes, so they are good. Now 8 is good, 7 is good, 6 is good because only one subtree. 5 is good because it has only one subtree. In the case of 0, here it has 1 2 3 4, 1 2 3 4, 1 2 3 4, so 0 is also good node. Now how can we approach this type of question, right? Now what one thing that you should have, the prerequisites to solve this question is recursion, depth first search, and post order traversal. Now what is post order traversal? Which means that first we are processing the children and there we are coming to the root, right? So here, for example, in this example, we are first counting the number of nodes here, and then we are checking for this 0. Okay, so we are gonna make a recursion tree here. So let's see how it's gonna be made. Okay, so in this example number 3, first we will go to the leaf. Let's say we are at 4. Okay, 4 is good. Now from 4 we will return total nodes that this 4 plus all the subtree nodes had. So that's 1, right? Let's just draw here using this online tool, pencil tool. Now 4 will be returning 1, 3 will be returning 1, 2 will be returning 1, right? So now 1 is a good node, right? So now 1 will be returning 1 plus 1 plus 1 plus the node itself, which will be 4. Same case here, it's returning 1, 10 is returning 2, 11 is returning 1 because it's the only node. Now here 1, here this plus this, it's 2, here it's 3, 6 plus 7 plus 8, so it's 3. Now here it's 4. Now 0 will be checked. For 9 it's 9 itself plus 1 plus 3, it's 4. So as you can see, for 0, 4 4 4 all are equal, so the answer is this node is a good node, right? So we'll count this node in. So let's try to make a recursive function for this first. Okay, before that we need to make a graph out of these edges. Okay, let's see the constants first. A and B are less than n, and all these points are 0 indexed. So this can be our adjacency list. Okay, now for all the edges, I hope you know this new syntax for C++. This is the more optimized and more user pleasant syntax that we are using here. Also, the root here, right? What is the root? Is the root always 0? Yes, root is always 0, which means that the root will be 0, and then we will go from root to the other nodes. Okay, graph a dot pushback b, graph b dot pushback a. A has children b and b has children a. Now function, now let's make a lambda function. Solve. Okay, this solve will give the total number of nodes for the subtree of any node. Like if I am checking for solve 1, okay, solve 1, so this will be, in this example 1, solve 1 will be 1 plus 2 plus this plus this plus this, solve 1 will be 3. Okay, now solve 1 is solve 1 is solve 4 plus solve 3 plus 1, right? These are all the children, right? So this is how we are gonna solve. Also, if I am at 1, let's say we are at 1, I don't want to go back to the 0, right? So if we are arriving at any node, we'll just mark that node as visible, right? So let's make a boolean vector, and here if not is this child, also here if is this node, if we accidentally arrive at any node which is already visited, we'll just simply return 0. Okay, good. Now here we are checking this. India child count is equal to 0. This variable means we are keeping track of the child count, right? So for example, if I am at 0, right, and I am checking for all the children for 0, first I have calculated for 9, which is 4. Okay, so I will just set this variable as 4. Now for the other children, I will just check if they are equal to 4 or not. If they are not equal, the parent element is not a good element, right? Also, we have to keep track of the total sum of all the children, because we have to return the total above, right? So we will also keep track of that. Total. Okay, good. Initially let's just mark it as -1, right? If we have not encountered for any children, if the child count is just -1, if child count is equal to -1, we'll just initialize it with temp. If also we have to mark whether this current node is good or not. Let's initially assume that it is good. We'll just keep on going thinking that this node is good, and if we come across any child that is not giving the sum as child code, we'll just make this bool as false. Right? Else if temp is not equal to child count is good is false. Right. Okay, good. And initially we have to keep track of total plus equal to temp. Okay, good. Above we have to answer equals to 0. Okay, good. If the node is good, if is good is true, answer plus equals to 1. Okay, good. And we can return total plus 1 because 4 plus 4 plus 4, and for this node also, like if I am at 1, so it will be 1 plus 1 plus 1 and plus for the 1 itself, so it will go 4. Right. Let's just recheck our code for any insanity. What is 0? Okay. Yep. Also we have to mark the nodes as visited also. Is visited. Like if I am at 0, I'll just mark it as visited. Now I'll just go to 9 will check for all the elements and not check for 0 because 0 is already visited. It will check all its children except 0. Same case for 1 will not check for 0, it will check for the other elements. Okay. Now let's just call for 0 and return the answer. Hopefully this should work. Let's see. But okay, and we have not declared n yet. Okay, is equal to, I have done edges dot size plus 1 because for any tree number of nodes is always number of edges plus 1 for any tree, and here we are given a tree, right? As you can see, undirected tree, so n will be edges dot size plus 1 always. Okay, this is not parent, right? So yep. S. Okay. Let's run it again, and I hope everything is okay. Yep, all the test cases are getting accepted, and now we can safely submit the code because I don't think there is any edge case that should be taken care of specially. Let's submit this code and hope for the best. Yep, our code got accepted. Now let's just try to analyze the time complexity for this code. Okay, now let's analyze the time complexity by taking example number 3. For each node we are arriving at each node exactly once, right? Let's say I am at 0. Okay, I will go to 9, then I will go to 5, and then I will go to 1 recursively. Okay, then if I am at 9, I will not go to 0 again because 0 is already marked as visited. I will go to 12 and then 10, right? So 9 is marked, 1 is marked. Same case, 1 will not go to 0, it will go to 4, 3, 2. So these are visited exactly once. Same case for 5, 6, 7, 8, 10, 11. So every node is visited exactly once. Okay, so in this code, if I am going to every node exactly once, and the computation for every node is just very simple, right? It's not any linear thing that I'm computing, so the time complexity will be big of n. and space complexity will also be because of the depth, right? We also have to consider the depth of call stack for any recursion, but the space complexity will be linear, right? So that's our solution. Let's check the complexity here. Oh, I have not upgraded to the premium yet, so it's okay, we already know. So this is our solution. I hope you like it, and see you with the next solution. Thank you, bye.